what we are going to see. R and C are called system parameters, and I is called the system output. VI is called the system input. Already we wrote the equation in terms of KVL. Now, if I transfer this, what it should become? VI of S equal to I of S into R plus 1 by C. This integral term will become 1 by S and multiply by I of S. Now we can take a common term. That's what you have done, correct? Here I is there, here I is there, this is C, this one. Now if I take this out, I can write VI of S equal to I of S multiplied by R plus 1 by CS. This is what written here. Why I am again repeating is, see here we are not shown I within bracket. This S is not shown there, this is not shown there. So don't get confused. If you understood properly, then every time you need not write. Additional writing is not needed.
I mean, 200 plus vehicles we had built. Nowhere we had print wheel. Only in one occasion at Mahindra we got this wheel, which was because of the damage during the fitment. It was identified, and once it is corrected, we did not get any wheel in the front side of in the complete history of development. But in this vehicle, 9.7 kilowatt frequency was observed. So I had asked Abhishek to stop the vehicle.
Anand, can you mute your mic? Hello? Yeah. Why?
Okay, I muted. Nobody can talk now because without my permission. So I just muted fully. Correct? Till the class ends, it will be muted. Okay, fine. Now that we have this Laplace transformed equation, and I can find the transfer function of this system. Okay, that is nothing but 1 divided by Ts. And already yesterday I told time constant is called T. Time constant T equal to R into C. For the capacitive network, you can find out from this. Yesterday just started with the second equation, second system, which is called as, this is called RLC circuit. RLC circuit. This is RC circuit because it has two components. In this case, there are three components. I have one resistor. I have an inductor, which is a coil. Third one is capacitor, which is supplied with input voltage from VA. Using KVL, Kirchhoff's voltage law, time domain equation equal to V of I is the input equal to, this is VR, voltage drop across the resistor. This is VL, voltage drop across the inductor, I call VL. This I call VC, voltage drop across the capacitor. So now the circuit is closed. This is called KVL equation, or voltage drop across the all the components equal to input voltage. So from this I take Laplace. This is time domain. First thing is, if you are asked to draw this circuit for this one, start drawing the circuit, RLC circuit, indicating this circuit you have to draw. Then you have to write the KVL in terms of time domain equation. Then you have to convert to Laplace domain. So Laplace domain again, here it is written as directly, but sometimes if you want to write properly, you say V of I equal to V of I S equal to I of S into R plus I of S into L into S. Please see that I is this variable, correct? I of T, that is converted I of S. That's what I returned. The L will become as it is, that is constant, that is inductance value. The d by dt of I is become S. So if I told you, if the function d by dt, it will become S. D square by dt square, it will become S square. Like this, if this d power n divided by dtn means it will be S power n. So that is what we have done here. Here for first derivative, correct? So it becomes S plus then I have 1 divided by C. C is the capacitance value multiplied by integral term is that become 1 by S. Already we saw in the previous case, multiplied by I of S. So this is what you have to write properly. But anyhow, here it is what we did is we are not showing every term I of S within bracket, that S term, to define it as a Laplace transform directly written. So this is Laplace domain, same equation. Now again in this equation also, my output is voltage across the capacitor VC. This VC is nothing but my output, input is VA. So that's what is mentioned here. That is what I wanted to find out. When I vary the input voltage, what will happen to my output? I wanted to find out. So then from this equation, I can find the transfer function. Transfer function is G of S is nothing but output divided by input equal to 1 divided by CS divided by I into R into S into L plus 1 by CS. Because we know that I is the, here you can see that everywhere I is common. That is nothing but the current flowing to sector. I pulled out. If I pulled out, that being I outside R plus SL plus 1 by CS. In the numerator, you have 1 by CS. Now, if I can reduce it because everything everywhere is common. So actually how we got this is I by CS in the numerator divided by I into right CS into R, because I want to have a common denominator. So CSR plus CS into S into L plus 1. Okay, common denominator CS. So the CS is gone, right? And now I can get this transfer function. Okay, so in that case, what I will have is I divided by I into RCS. I am just rearranging term RCS for easy understanding plus CL into S square plus 1, which can be written like this. By removing the I and I will get 1 divided by S square is the highest term. RCS is the next term, this one. So we got the transfer function. Please take the equations and derivations, because in exam you may be expected to derive show the circuit diagram, RLC circuit, derive the time domain equation, find out the final, the transfer function. That means all the steps you have to show. Step by step you have to do. Then find out delta, which is called a damping ratio. Note down. This is called damping ratio of RLC circuit. Okay. And this root of, in this equation, this denominator is root of 4 by L by C is called as critical damping CC. It is called as critical damping CC. So I can write delta equal to R divided by CC. Do you remember in the previous class we are talked about delta of the spring mass damper system, correct? Delta was KD divided by CC, where CC equal to root of 4 MK. This was we written in the previous for the spring mass damper system. Please see that this is called as first order system. This is called as second order system. RLC, the spring mass damper system also is a second order system. Why? If I write the time domain equation, correct? So the time domain equation V I of t equal to I of t into R plus L into d by dt of I plus 1 by C, this one. Because this contains a algebraic term, that is I multiplied by R plus L into d by dt I. This is a differential term. This is an integral term. So that's why this is called integral differential equations. Of course, automatically there will be an algebraic term also. And if you want to solve this, generally what we'll do is we'll convert this integral differential to pure differential equations. How will you do that? Do a one-time differentiation. If you do one-time differentiation, what you will get? You will get I of this I of t will become di by dt into R plus L into I of t plus 1 by C into I of t. This is what this one. Now, the highest term in this is d square by dt. Next term is d by dt. Last one is just algebraic solution. So, the integral differentiation converted into a pure differential equation. Pure differential equation second order. So, if you have a second order system, the second order system will have a damping ratio. Correct? Please note that when we talk about a mechanical system, we'll talk about damper. What is damper? Is nothing but frictional system. Friction or frictional system called as a damper, which produces opposing force. So the damper we use in this. What is job of damper? Job of damper is to absorb the energy. When we talk about mechanical thing, we saw that one is damper, other one is spring, other one is a mass. Damper is energy dissipating element. Spring is potential energy storing device. Potential energy storing device. This is a kinetic energy storing device, mass element. Similarly, in case of our electrical circuit, R is energy dissipating element. L is kinetic energy storing device. C is potential energy storing device. So same, equivalent. So R in electrical circuit equal to damper in mechanical system. Both are energy dissipating. So now we are converted into differential equation. Then only here also we could do the same thing. If I do this one, you will get the transfer function. In this case, what I am targeting is right now we tried as it is directly from the integral differential term by term we converted. From that we got the transfer function, final transfer function this. So this is called as damping ratio. This is called as critical damping. Okay, this is called as critical damping. So if you may ask to find out what is the damping ratio of electrical RL circuit and also find out critical damping, provided when I give C equal to so many this much, R equal to this much, L is this values are given, then automatically you can find the transfer, you can compute the transfer function and also you can calculate these two parameters. Take this. Now we'll see another example for the electrical system is motors. Motors are used widely as actuators in many mechatronic systems. There are many wide variety of motors are there. We'll see when we talk about actuator. When we say motors, electrical motor we are talking. Already we saw hydraulic motor and similarly pneumatic motor both uses compressed air and compressed liquid. Hydraulic motor compressed liquid. Pneumatic motor is a compressed air. We will see all those things when we talk about actuators. If I talk about motors, that is electrical motor. In electrical motor, I can classify as a DC motors and AC motors. Right. Next one is AC motors. Right now, we are going to talk about a DC motor, which is called a actuator. There are two types of DC motors are available. One is called field control DC motor. Other one is called armature control DC motor. If you see any motor, correct, any DC motor, it will have two coils. One coil called field coil, other one is called armature coil. Can see? Okay, the armature coil. Please note that theoretical coil means nothing but inductor. That is shown like this. So it should have only inductance value. Inductance L is symbol, letter representing this one. I say this equal to 10 henries, the unity henries. Correct? Or 2 henries, or 5 henries, or 0.1 henry, which can be sold 100 millihenries. Correct? Like that, a coil will have inductance. Inductance value varies in terms of henries. Correct? Now, we know that motor also going to do one is called armature coil, other called field coil. Coil means automatically will have inductance. But the pure theoretical inductance, only have inductance. It should not have R equal to resistance. Already you know the fundamental building block of an electrical system is resistor, capacitor, inductance. Pure inductance should have only inductance. No resistance should be zero and capacitance should be zero. That is for theoretical inductor. but we do. How will you make inductor practically? You need to take a wire, correct, having some length, and the wire as a cross section area. For example, wire is copper wire. Correct? I say that I have a copper wire like this. Correct? It is a solid wire. That means being a cylindrical shape. Okay, that means it has a radius. If radius is there, automatically you can find a area. It is area of circle. Then it has a length L. It has an area. It has a length that is L. That is length equal to L. Then it has what you call a resistivity. The wire material has resistivity, which is generally represented by rho symbol, the Greek symbol. The rho value will be varying for different material. In periodic table, you have copper, correct? Metals to take aluminum, copper, iron, correct? Platinum, rhodium, gold, silver, like this, correct? Or any other material in the periodic table will have resistivity. The resistivity is different for each material. For example, this wire is made of copper, Cu, correct? Cu rho may be 0.0015 ohms per meter unit length. So this is called, this you can find out in the Clark's table. Correct? Many books are available where various parameters are indicated, constants, correct? Unit conversion, all those things. In the book you will see they will show about this one. For example, if a copper wire, rho is there. Now you know the cross section area, you know the length of the wire. I can write resistance of the wire equal to rho L by A, where rho is the resistivity of the material. Copper I showed. If it is silver, it may be 0.001. If it is gold, 0.001, something like exactly. I don't know. I try to give some example. Each one has a different. Please know that gold is the best conductor or better conductor than silver, and silver is better conductor than copper. Copper is better than aluminum. Correct? But gold, you cannot make gold wire for electrical thing. Very expensive because availability is not there. But it is one of the best conductor, and the power loss will be very less. If resistance is less, resistivity is very low, the resistance will be low automatically. Power waste and the wire will be less, but it is very expensive, not a rare metals. That's why we are going for copper. Copper is the best material for making electrical wires, and relatively available more in abundant. There are billions of ton available. Gold available is less than 1 million ton in the entire earth. So that's why you cannot go for that. Now, if you know the resistance, that means what I wanted to say is, here I have shown the armature coil. This is armature coil, and this is the field coil. Two coils are there. The armature coil will be wound over a rotating this one cylindrical object. Correct? That is it. Now, and the field coil is in the body of the motor. Okay, if you see a motor, I'm just approximately showing, correct? This is body, which is fixed on this one, and in which, and so here you have the coil. In the body, you have a coil, it is coming out. This is called field coil. It won't move. Correct? Body is fixed, and it is a cylindrical shape, hollow cylinder, and the periphery of this one, coil is fixed. Then you have the rotating part called as armature. Armature also will be made of cylindrical material, correct? But using magnetic material, laminations, and on which there will be a coil. There will be a coil. That coil is called as armature coil. This is called as armature coil. And this is put over a shaft and bearings, supported by bearings. So the shaft is coming out. So the rotating part is called as armature, on which there is a coil, armature coil. The fixed coil, field coil, is on the body of this one. Now we have to give voltage to both. That means I have to supply voltage to armature, I call VA. There's a current flowing IA. Then because of there's a magnetical phi A. When you know that in electrical circuit, according to Ampere law, when current is flowing through a conductor, if there's a high amount of current, there will be a magnetic will be created. That is proportional to current. But current is proportional to voltage. Voltage per a given, then how much current will flow? We know that if we take a wire, that's what we are talking. R equal to rho L by A, where L is the length of the wire, R is resistivity, A is the cross section area of this one. Now, if for a given wire material, copper, the rho is fixed. Rho is fixed. Right? And then only two variable is L and A. If thicker the wire, area will be bigger. If longer wire, length increases. Length. So if I vary any one of this, the resistance of the wire changes. This is for pure wire, correct? Or conducting wire. Now, if I want to make a coil inductor, for that you have to use wire only. I took a wire, long wire, for example, say 100 centimeter, correct? Made it as a coil. That means this is wire. I made it as a coil. Now it become inductor. The wire is converted to coil, automatically become inductor. It has inductance value. Wire has resistance, correct? So as a copper wire, according to this formula, there's a resistance depending upon the thickness of the wire. Okay, that is the cross-sectional area, length, and resistivity. That's resistance. That same wire will now conduct an inductor. That become inductance. So this is called practical inductor. This is called a practical inductor. In the practical inductor, the inductor is there. It have inductance of L, but it also will have resistance because you are made of some conducting material, right? Copper, gold, whatever may be. Any with this one, they have resistivity. That means in theoretical inductor, inductance alone will be there. R will be 0, capacitance will be 0. Correct? This may be 10 Henrys. But practical, this one, it will have inductance plus resistance. This is called an equivalent circuit. Note down. In electrical engineering, they call equivalent circuit. It is not a pure inductor. Like only have inductance. It has, since you made this inductor using a electrical wire which has a resistance. So that means that will have resistance plus inductance together. So now this, that's what we shown here. You can see that this whole thing represents the armature coil. Armature coil has some inductance because it is made as a coil, copper wire, but copper also has resistance. That resistance called Ra. Similarly, you have field coil. Field coil also again making copper wire, so it has a inductance plus the resistance of the coil wire. Please note that don't think Ra and Rf is separate and additional resistance. This is the resistance of the coil itself. So together only you have to consider as the armature coil. Armature coil. This is called as field coil. Okay, so you can't avoid because you in the periodic table you don't have any material which has zero resistance. Only possibilities if I want to have a motor whose armature and field don't have Ra and Rf, means I have to take a superconductor. If I take a superconductor and make a coil, that will be a theoretical coil. It will have only inductance, say for example 10 Henrys, and R will be 0. Only if I make a superconductor, correct? But not possible. Room temperature, no superconductor, you have to cooling all this thing. So no motor, maybe special purpose motor may be there. Still, it may have very low resistance, going to absolute 0. Correct? At 0 degree Kelvin only, the resistance R will become 0. That is what superconductor. But making to any metal close to, we go to close to 0 degree Kelvin, not exactly 0. Impossible. It requires tremendous amount of energy. So we say approximately become 0 degree Kelvin. We say that already superconductor, but people are trying to develop the materials which are superconductor 0 degree temperature, that is room temperature, 30 degree, 35 degree itself. Correct? If you are able to succeed, then it will be a lot of research going on worldwide for the last 50, 100 years. That's different. So this shows about my field control DC motor. I told you there are two coils. One is called field coil, other one is called this one. Now, if I give voltage to VA and VF, there are two inputs. Both the coils should be supplied to this one. Then if I supply this one, there will be a current called IF and there will be a current called as IA. This is called as armature current. And this is called as field current. Okay. So now, because there are two currents, there will be two magnetic fields are created. One is called field magnet. A field magnet strength, I say phi A. Correct? Generally, we use Weber or Tesla is the unit for magnetic field strength. We will say the Weber, correct? So, so I say that because IF current is going, this one, there will be a magnetic field phi F, and that phi f is so many Webers. Similarly, there's IA current is going because we have supplied input to VA. So that means there will be a phi A amount of magnetic flux. Once two coils are supplied voltage, two magnetic fields are created, repulse each other. So the fixed part, coil, which is in the body of the motor, will not rotate. And the armature coil put on a rotating component with bearings. So the armature start rotating. Armature start rotating. The rotational force developed by the motor is proportional to the we call it torque. That I said TM, motor torque, equal to Km into IF into IA. We know that IF is called as field current and IA is called as armature current. And I can write this again as TM equal to Km into phi F multiplied by phi A. This can be written like this also. We know that now the current flowing IF equal to VF divided by RF. Similarly, IA equal to VA divided by IA. Okay. So now if I vary the coil already we made, correct? The armature coil is made, field coil is made. So the resistance RF and RA is already fixed. RA is fixed. What I'm varying? I'm varying input of VF to the field coil and VA to the armature coil. Automatically, if I vary this, IF will vary. And similarly, IA will vary. If these two are varying, phi A will vary, phi F will vary. If varies, according to this formula, the torque produced by motor is varying. That's what we want to say. Now, we want to develop the mathematical model of the motor, field control motor. Why this is called field control motor means we can see that that a torque produced by motor, TM, I call as equal to Km into IF into IA. Km is called as motor constant, no doubt. It is called as motor constant. That will be given by motor manufacturer. Okay. In the exam, for example, we ask some problem, something, write the final transfer function of the field control motor or armature control. I will give Km, I will give IA, I will give, correct? RA I will give, LF I will give, all the values are given. Then you can form it. So now the motor, there are two coils. If I vary VF or VA, please note that VA and VF should be greater than 0. Then only the motor will work. Both should be greater than 0. You can, so VA equal to, for example, 100 volts. VF equal to 0 volts. Okay. You give. What will happen? TM according to this equation. Correct. We know that. And RA equal to 10 ohms. RF equal to 10 ohms. Right? If it is given, then we can find out what is the IA and IF. And that is nothing but IA is VA divided by RA. Similarly, IF equal to VF divided by RF. One that is known, then I can substitute the value here and the motor constant or Km is given. Km equal to, I say that 0.05, something like that. Then you can find out torque. But if any one of the value, correct, VA or VF is 0, here IA or IF will become 0, automatically this whole torque will be 0. That's why what I'm saying is you need to supply voltage greater than 0 for both the coil. Many times, if I wanted to control the speed of the motor or torque of the motor, torque is generated by motor is proportional to current supply. So this is TM. Current supply by the armature coil and the field coil. This is going to be constant. This IF and IA will vary by varying this voltage. If I vary this, instead of that, that means I can control the torque of the motor. And if torque is available, then the omega motor speed is proportional to torque of the motor. Higher the torque, and if the torque is more than the frictional torque, then the motor speed will increase. So the omega also proportional to TM. TM in turn is proportional to current supply to a field and bore coil. What I do is in field control motor, VA will be constant voltage. For example, I give 10 volts, correct? Because there's a current with RA equal to 10 ohms. LA equal to, for example, 5 millihenries. Many times it will be very small, not even henries, very small. So it can be neglected, correct? It can be neglected for the current calculation. I can say that IA equal to VA divided by RA is going to be 10 divided by 10 equal to 1 amps. So now there's a constant current is going in the armature coil. That means IA is constant. IA equal to 1 amps. So phi A is, for example, 10 Webers. There's a formula I'm just giving for understanding purpose. That means there's a constant magnetic flux. In this case, for calculation, IA itself sufficient. IA is substituted. That is, this is 1 always. Km equal to, I said 0.5. I have substituted. What I'm doing is I'm varying VA 0 to 10 volts. And I know the RF equal to 10 ohms. Okay, then I say IF equal to VF divided by RF. Okay, VF I'm varying from 0 to 10 volts. RF is constant, 10 ohms. In that case, what will happen? IF will be equal to 0 to 1 amps. So in this equation, TM equal to 0.5 multiplied by 1 amps IA. This is nothing but IA, armature current, that is constant because I'm keeping armature voltage constant. So I'm varying, only thing is multiplied by IF. IF is varied from 0.1, so 0 to 1. So in that case, you will see that TM will vary from 0.5 to 0 to 0.5. Correct? The torque will be so many Newton meter will be varied. That means my motor torque varies when I vary the field current. So this is called a field control motor. For this, if I want to develop mathematical model, another important thing what I want to say is in case of motor, again there are two coils. One coil is fixed, other coil is supplied with variable voltage. One is fixed. In this case, here I am supplying fixed over 10 volts. Here I am varying 0 to 10 volts. Then I call this a field control DC motor. Then now I want to develop a mathematical model of this motor, correct? This field control DC motor. So this one I can be this part become a fixed, correct? This IA become fixed. I need not worry. Only thing is the field coil where I am varying. So the voltage applied to the coil is VF. So this is input voltage. This is according to KVL. That because of there's a current flowing happening IF. So that current is flowing through this resistance and this inductor LF. Correct. So this voltage I call VF. Sorry, VL, and this I call VR. So V field voltage applied. This is input equal to the voltage drop across the field resistance and voltage of field inductance. So this can be written as R into I plus LF into D by dt of IF. IF is the current flowing here. Okay. Now this is time domain equation. This can be converted to Laplace domain, correct? That is nothing but VF of S equal to RF into IF plus LF into D by dt of is become S into IF, right? So then I can say V of S equal to LF. So IF I can take it outside because RF plus LF. That's what it will become, right? So now LF into S, because S is there. This will remain. So now I can write the transfer function. For the transfer function for the field coil is nothing but IF divided by VF. This VF is input voltage, IF the current output of the system for the field coil. That it can be written 1 divided by LF divided by S plus RF divided by LF. So now, if whenever I talk about motor consists of two parts. Please note it is only a single motor physically. But when I consider analysis, there are two parts. I am giving input voltage VA, correct? Due to this, there's a current going IA inside the motor. This is called as IA. And then electrical part is this. Correct? The resistor and inductor is called electrical part. Already we have the transfer function of that part. What is transfer function? 1 divided by LF divided by S plus RF, this term. This is what we are talking. So RF divided by LF. Now, if I supply this voltage, IA current is going. Because of that, what is the output of this system? TM. Torque is the output of the system. Please see that torque is developed by this electrical circuit. Now, this is given as an input. The torque developed by the electrical circuit given as an input to the mechanical part. Mechanical part is nothing but the armature has a mass. It has some friction also. That part is called as mechanical part. So the mechanical part equation can be written like this. Okay. Summation of the moments equal to Tm minus C minus Cw equal to J omega, where J is called as moment of inertia of the armature, which is rotating part. C is the friction, bearing and other frictions. So I can say that Tm is the input torque for the mechanical system. This is mechanical system. This is electrical system. Please don't think that there are two separate. Only one coil you supply voltage because of magnetic flux, because of that torque is produced. The torque is given as input to mechanical system. Then if I write the transfer function, this is my mathematical model mechanical, correct? J omega to omega dash. Omega dash is nothing but acceleration, angular acceleration, alpha. Alpha equal to d by dt of omega. That's why it can be written as omega dash plus C is the damping into omega, angular velocity equal to Tm. Now, from this I can find the transfer function of mechanical system. What is the output? The angular velocity of the motor speed divided by torque generated by electrical circuit Tm equal to 1 divided by J divided by S plus C plus J omega. Because this is in time domain, correct? Again, I can write the Laplace. J into omega dash is nothing but S square, correct? S square into omega S. Okay. Let me clear this. So from this I can write J into S square into omega S plus C into omega S equal to input, correct? Input is Tm of S. So that's what, from this I can get the transfer function. Transfer function nothing but output of the motor is omega, angular velocity, divided by torque input to mechanical system, which can be 1 divided by J plus S, this one. Now, these two can be combined because we know that the electrical system is there, mechanical system is there. Here the omega S is the output. Here is the VA is the input. So I can combine both the transfer function. Which transfer function? This plus this. If I combine, I get the final motor transfer function. Output shaft speed divided by input voltage, field control voltage equal to omega S into TMS divided by TM into VFS, which can be written in terms of KM, correct? Here already motor constant, divided by LF into J, divided by S into C by J into whole thing multiplied by S into RF divided by LF. Now I can write a final equation, omega, I can write in some theta also, correct? Angular velocity and theta both I can write. If I write like this, theta divided by input voltage equal to theta S divided by omega S into omega S divided by VF. So I can write like this final transfer function. I think we will ignore this. Right now you take this. Okay. So motor speed divided by input voltage. This is nothing but G of S. Transfer function equal to Km divided by LF into J and S into C J divided by S plus this one. Now, if the LF is given some XX value, J is given YY, correct? And C is given XZZ, and RF is given, say AA, correct? KMF is given BB something, correct? And ask you to write the final transfer function, means you can substitute all this thing, find it. You will get one numerator term, a constant. This will become a constant, correct? This will become a constant value divided by, in terms of S square plus something plus S into something plus some constant value. This will be your final transfer G of S. Okay, so this is called field control motor. Instead of that, I can have armature control also. Both way I can control the motor, torque and motor speed. Okay, omega. So in the armature control, what I do, field I give a constant, VF will be 10 volts, constant voltage. I'll vary VF will 0 to 10 volts. Same, exactly same, only thing I am varying. So then you can see the same equation only we are talking. Only one small thing with the armature control is, you will see here, the VA is the applied voltage, correct? This is the applied voltage. This is going to be, that means this term is have a fixed current. IF is there, and I am not even discussing. It is there. Please know that this IF is there, but it is going to be a constant. What I have is motor constant. This is also constant. Only variable is IA. If I vary the VA 0 to 10 volts, the IA will vary 0 to some X value, amps. So automatically TM will vary. Now, while writing the equation, so transfer from G of S equal to TM divided by IA equal to KMA. Okay. Now, here you can see that VA is the applied voltage, correct? Armature voltage equal to RA into IA multiplied by LA into D by DT of IA. This is VL. This is VR. There's one more voltage is there in the generator in the armature itself. That is called a back EMF, VB. Note down. VB is called as back EMF motor. It is called as back EMF motor. So in that case, you will write the transfer function. Before writing transfer, first you have to write the mathematical model using KVL. So this is the mathematical model of the KVL. So that means for understanding, I will draw clearly. I have VA. See, this part is already, this part is already there. Constant IF is constant. So the constant where IF is flowing, for example, 10 amps or 5 amps, whatever may be, fixed. So that means being a constant, I'm talking armature control, controlling motor speed by varying the voltage 0. If armature voltage becomes 0, even IF equal to infinity, correct? This value is infinity, this becomes 0, torque becomes 0 automatically. So that's why I'm controlling. But we are not going to have the infinite amount of current. When the field coil, that also limited, for example, 10 amps current or 5 amps current, whatever may be. Correct? That is done. Now, when I write the mathematical model for this is this one, we need to write, take down, this is my VA, supplied voltage. This is my RA. I will quickly come to, I know that you have the next class. Further, you have what you call as a back EMF, V back, which is generated by the armature coil. See, please know that there's an armature coil which is rotating inside the phi F. There are two magnetic fields, phi A and phi F. Phi A is constant and depending on voltage, and apart from the, sorry, this is phi A. Phi F, this is phi A. Okay, so this is going to be constant, and this coil is not rotating. Correct? It generates a phi F, and because in the body is this one, but armature is rotating inside this magnetic field, phi F. Correct? Armature generates its own phi A magnetic flux because you are supplying a voltage. There's a current IA. Apart from that, in the armature coil, a voltage VB is generated because the coil, armature coil is rotating inside the phi F. You know that if a conductor rotates in a magnetic field, it will generate voltage. That is what gets generator. Correct? Generator is nothing but electrical generator. If a conducting wire rotates or moves inside a magnetic field, a voltage will be induced. Correct? That we call as a generator, induced voltage. So that induced voltage VB. Only thing is the VB is opposite to supply voltage. That's what is written here. So this is plus minus. According to this, VA equal to VB plus IA into RA plus D by dt of IA into LA. So this is nothing but VL. This is nothing but VR. This is the back EMF. So I can write this equation VA equal to VB plus VR plus VL. That's what we written here. This term will not be there in the previous. Please note down here. We don't have the term VF, VRVL. Back EMF is not there. In case of field control motor, in the armature control motor, that comes into picture. So for that, if I write the equation, this will be Laplace domain, correct? So I can say that VA T minus VB of T equal to IA of T into RA plus LA into D by dt of IAT. This is the time domain. And if I convert, this is Laplace domain, correct? I convert to Laplace and I can take out IA separate. Then I can write the equation, correct, transfer function for this, for the electrical part. That is nothing but Tm divided by Va. You'll get the equation. Okay. So that is going to be 1 divided by LA divided by S plus RA divided by LA. This is what you are going to get. Take the Laplace and take the transfer function for electrical part. Then this torque is given to mechanical part. For the mechanical transfer, already we saw same thing only, whatever we saw here. So the final transfer function, I just wanted to clear everything. The final transfer function is nothing but angular velocity of the VA armature, which is a shaft speed, input to VA. If I vary, this is finally take the equation. This can be represented as this block diagram representation. I'll stop here. Correct. So tomorrow we have class 5 to 7. I will be taking for 2 hours. I told you, correct, because we wanted to complete some syllabus before our midsum exam. Okay. Any doubts? Let me unmute.
Sir, I have a question.
Yeah.
Not with respect to the class of today, but I was just going through the books, whatever is there. Sir, which would be a better reference to read about the current concepts, whatever we are reading?
Yeah, actually, I told you, because this for this there is no specific book. There
Yes,
are
sir.
books. There are few books available mechatronics. But introduction, did I show you introduction to mechatronics? That course,
Sir,
any books, I reference books.
about an article by Mr. Ashley, the 14-page article. There is a. I
Okay.
think yes, Ashley, you had shown one slide from one of the PPTs.
Yeah, what are reference books?
Yes, sir, you had shown. One of them is yes, Ashley,
Okay.
Introduction to Mechatronics.
Yeah.
One more was
Dev City, something
David
like
City
City.
and R.A. Polk.
Yeah. So,
And one,
yeah, please go ahead.
sir, and one more book that you had referred was mentioned was one by Mr. Bolton, W. Bolton. William
Yeah,
Bolton.
W. Bolton also. Yes, yes.
Sir, actually, one thing I observed, sir. So there are 2 books that you have mentioned about Bolton. So in the class, whatever you had mentioned, sir, it is electrical control systems and etc. by William Bolton. And in the syllabus, what you had you had shared, sir. There is one more book alongside that book called as Mechatronics Systems by Bolton. So should we refer both or just the one is enough, sir?
Anyone, see, I will tell one more thing more importantly, because the mechatronics is growing field, new field. What I am teaching, I am referring more than 5 to 10 books. I teach many subjects. I told you I am not a mechanical engineer. I teach control system. Control 5 to 6 books are there. I will talk about digital electronics, operational amplifiers, microprocessors. This course I am talking many of things. What I am showing in the slides is from more than 10 to 20 different resources. I am teaching the course for the last 22 years, you won't believe. Correct? So I refine, change, add new things. There's no single book available. That's why I'll tell, please attend the class without missing. Take the notes, what I am not only showing on slides, what I'm discussing also. Correct? Important point you note down, then only you will get a good score. Those are reference books only. None of the book covers what I'm teaching. For 40 hours, I'm teaching different topics, which I collected from various books for the last 20 years. Because apart from that, I'm studying different subjects, different control, instrumentation, sensors. I teach full courses. Instrumentation also BTech, 52 hours I teach. I taught for 14 years. Correct. For that, I refer 5 to 10 books. Correct. Then I talk about operation amplifier, analog circuit. I was teaching one course. And sensors, I talked about one course separately. Microprocessor detail, I can teach one course. In IIT, last 23 years, I am teaching more than 10 different courses. All electronic control, instrumentation, detail electron, microprocessors, embedded systems, like this. So, do you know what you are seeing? Mechatronics is condensed version of many fields. That's why I tell this is field is a mechanical. I am teaching robotics for last 8 to 10 years. Correct? Dynamics, kinematic, all these things. So they're full course. I'm teaching a 40 to 44 hours. So from each one, I take important to make you to understand. Please note that this course is introduction course. You need to cover everything and the basics you should be clear. That's why I explain more instead of showing hundreds of slides. Many times, many processes may show a lot of equivalent derivation, but here understanding concept is very important, and each concept different. Sensor is different, mechanical modeling is different. Microprocessor we are going, then a control system we are going to talk about. Laplace transform you should know. Correct. So please take notes, and whatever I explain also you take as a notes. Correct. Just if you show in the exam, if you just show what is shown in the slide alone. If I ask a question, explain RLC circuit model, all those things. Using KVL, derive from the basic, this one, write the transfer function, find the time constant, all those things. I told the equation also that important part you have to write. If I give a 5-mark question, just writing the 4 equations, this one will not get 5 marks, I'll give only 2 marks. Correct? But so that's why you have to attend classes without missing and take notes also. Those are reference books only. There's no one book which has whatever I'm teaching for this whole course. This is taken from 4 to 5 courses. Each course there are 3 to 4 books. That will be very difficult for you. That's why I tell the student systematically attend and take the notes. That will be good for you. Okay.
Thank you, sir.
Thank you. See you tomorrow by 5 o'clock. Okay.
Thank you, sir.
Thank you,
Sure,
sir.
thank you, sir. Thank you.
Okay.